picking up where I left off, this is part 3 of my set of videos on steady state error. We stopped at this slide here. So we've had two explanations of why steady state error arises. One practical explanation with a cruise control on a car, and now this is a more abstract explanation using block diagrams with a plant that is a first order plant. Okay, continuing on from here, we can actually calculate these numbers. I give some values for Kp, Ka, and K. These are just random, picked for convenience, just to show the example. So if Kp is 1, Ka is 1, and K is 1, then this will be 1 on top, and this will be 1 here also, and then the KCl will be equal to just 1/2. So if we remember what R is and what C is. R is our desired value, and C is the actual value. So if we tell the desired value to go up by 1, it's not going to go up by 1. It's actually only going to go up by 1/2. So it's not, we're going to have some steady state error. Now, what I did was I actually ran this example. I put in a time constant of 10. That's just kind of random too, just to have an example. But I have a unit step input that I put in here, and I've closed the loop around the inner first order system. Now I've not put in K, P, and Ka because they're both 1, so I've just included them both in our system here. And then when I run this, I tell it to go. I tell the step to go from 0 to 1 at 5 seconds. But notice that the result is it only goes up to 0.5. So the steady state error here is the difference between where it did go to and where I wanted it to go to. So it went up by 0.5, but it's shy of where you want it to go by 0.5. So it only went up 1/2 unit, and that's what we predicted in our analysis that it would do. Now, where does this error come from? I've already explained this somewhat, but we'll do this in a little bit more detail here. Here is my loop. In a general sense, here I can have an h that's not 1, although this works also for h equals 1. And then I work out the algebra here. E is just equal to r minus b, and then b is equal to h times c, and then c is equal to g times e. And I can put all these together. So I can put this b into here, and then I can put this c into here. And when I put all that together, oh, sorry about that, I wind up with an expression for E. This is a little, I think we've worked out the, or in another video I've worked out the closed loop transfer function for this, but what we've done here instead is we've actually worked out the expression for the error in terms of these other signals. So as you can see, the error is, it depends upon the input, R, but it also depends upon this 1 plus GH. Now, GH actually has a special meaning. I think I give that in the next slide. Maybe not yet, but I will in a minute. To analyze this, we're going to have to use something called the final value theorem, and this is covered in chapter 2 of my book, which is focused on the Laplace transform. But anyway, the Laplace transform is a tedious analytical way of converting from the time domain into the S domain, or converting differential equations into algebraic equations. And the problem with that system is you convert your differential equations into algebraic equations. You solve the algebraic equations, and then you have to reconvert back into the time domain. And that process of converting from the S domain back into the time domain is called the inverse Laplace transform. But there's a way around that if you're satisfied with limited information. oftentimes you don't care about the dynamics of the system, you just care about where the system is going to wind up. And for that reason, you have something called the final value theorem, which says it's a relationship between the t domain and the s domain. If you want to find the final value of your system in the time domain, but you don't want to go through the rigmarole of converting from the s domain back into the time domain, you can use this theorem. And what it says is that the equivalent of t going to infinity in the time domain is the same as s going to 0 in the s domain. But there's one little difference here, and this is something that is an easy mistake to make. There's an extra s in here. Now, I have not derived this. If you want to see the derivation of it, you can go look at it. I just simply know what it is, and it would take me some time to come up with the rationale for this, but I just know how it works, and I know how to use it, and that's good enough for me as an engineer. So I caution you here, don't forget that extra s in the theorem. Now, this extra s actually plays a big role in our topic of steady-state error. So the version of the final value theorem that applies to us for ESS is this relationship here. We're interested in E as t goes to infinity, and we call that ESS. SS stands for steady state. What we do is we get the expression for the Laplace transform of E as a function of t. We put it in our formula, we multiply it by s, and we let the s go to 0. Now here, yeah, I do note that GH is equal to, there's our formula there. This is actually our formula for ES, and I put that in here. The GH, like I say here, is actually defined as the open loop transfer function. Why? Well, that's just the way it is. Actually, if we go back and look at, is it here? No. Yes, if we look at our block here, our closed loop transfer function is C divided by R. So it's this whole box, right? Or you put this whole thing in a box and you work the formula. There's our, no, this is not our formula for open or closed loop transfer function because we solve for E. But our open loop transfer function is you go from R, you open the loop by cutting it here, and then you go around the loop through H. So our open loop transfer function is G times H, or the other way to say it is B divided by R. It's always output over input, or it's the two blocks multiplied together. So let me get back to where we were. The error depends upon the input. Obviously, the R is in there. And we will consider it depends upon the input, and it depends upon the open loop transfer function. So we're going to consider 3 common inputs that are put into systems, and I'll talk about those next. And I think what I'll do before I do this, I think I'll just start a new, I'm not at 10 minutes yet, but I'm close enough to it. So rather than getting into that, I will just talk about our 3 inputs. We're going to put a step input in, a ramp input, and a parabolic input. I'll start on this and then I'll continue it in the next slide. A step input is just you're at 0 and then you jump up to a new value R0. This is like flipping a switch or turning on a light. Well, turning on a light is flipping a switch. Opening a valve, stomping on the accelerator, which opens a valve. All of a sudden. This is a little bit different in that you don't do it all at once. You do it gradually. So you slowly open the valve at a steady rate. With a light switch, that's kind of hard because that's a binary device. But if you had a dimmable switch, for instance, turning it regularly so that you increased the voltage going to the lights, that would be a ramp. And then the parabola is a little bit like the ramp. And it actually is a common type of thing to do. If you don't know the reaction of what your system is going to do when you change the input to it, so you change the excitation, you might start off slow and let it get going, And then as you gain confidence that you know, everything's going to be okay, you just keep turning it up so that you get a higher and higher level as you go along. So this is kind of like a cautious ramp is what it is. Don't put the ramp in all at once. Well, the ramp is like a cautious step. But the parabola is, well, let's give it a little bit at the first, and then as things are okay, as we see things that are okay, we'll just continue to increase it. Okay, I'm over 10 minutes now, so I'll stop here and I'll start up with my next one in just a minute.